I would like to thank everybody who is attending this webinar today. The webinar is really bringing in two top scholars in their field, both Dr. Hussein Hoteit and Dr. Kassem Ghorayeb. The webinar is on CO2 capturing, storage, and sequestration, the cases of Kingdom, Saudi Arabia, and Lebanon. In particular, this is part of a project that has been funded by the American University of Beirut and by KAUST, King Abdullah University of Science and Technology. At AUB, it was a Masri Institute project, jointly also at KAUST also is supporting that same project in Saudi Arabia. I'd like to present the first two speakers, the two speakers, and then we will give the floor to Dr. Hoteit. Dr. Hussein Hoteit is an associate professor in reservoir engineering and the energy resources and petroleum engineering program. He is actually the chair of the energy resources and petroleum engineering program at King Abdullah University of Science and Technology. Before joining KAUST, Professor Hoteit worked for ConocoPhillips and Chevron companies for about 12 years, where he conducted projects related to chemical EOR, CO2 EOR, steam flood, EM heating, and others. Professor Hoteit's current research includes chemical EOR, geological CO2 storage, IOR optimization, data-driven modeling, and reservoir simulation development. He has earned several Society of Petroleum Engineers awards, including SPE Distinguished Lecturer in 2009, and served as Associate Editor of the Society of Petroleum Engineers Journal for more than 10 years. So we welcome Dr. Hoteit. And now I will present also the biography of our second speaker from AUB, Dr. Kassem Ghorayeb, who joined the Department of Chemical Engineering and Advanced Energy in August 2016, after a long journey with Schlumberger, where he held senior technical positions in the UK, Saudi Arabia, Kuwait, and the UAE. Kassem's research focuses on field development planning, optimization, and CO2 capturing and sequestration. Dr. Ghorayeb is still active in the industry as a global reservoir engineering and field development planning advisor at Schlumberger. In this position, he contributes to challenging FDP projects and integrated reservoir studies, in which roles include hands-on reservoir engineering, team leading, business development, peer review, and mentoring. So now we're going to give the floor to Dr. Hussein Hoteit to talk about the overview of the geological storage potential of CO2 in Saudi Arabia. Dr. Hoteit, the floor is yours, and I really want everybody to keep the questions after we listen to the two presentations. Thank you.
Thank you very much, Professor Ghaddar. And first of all, can you see my slide? I shared it already.
Yes, I see the slides, and I assume all attendees do.
All right,
as well.
Excellent. All right, good morning, marhaba everybody, and it's really my pleasure and an honor actually to be with you. And I really thank AUB Masri Institute, Professor Ghaddar and Professor Ghorayeb for this invitation. All right, so today I will talk about some activities related to CO2 storage within the Saudi Arabia. Before that, all right, so this is the outline for my talk. I will briefly show the current climate and energy scene. I know this will be maybe the obvious, but it's always good to remind ourselves what's going on. And then I will talk about get into some details related to the emissions, CO2 emissions in the Kingdom of Saudi Arabia, and the current activities related to CO2 geological storage, and some closing thoughts about the path forward. All right, so what's going on right now? All right, so if I look at this chart here, it shows the CO2 emissions. This is in metric tons. So this is about 35 billion metric ton currently, the world CO2 emission. And this is essentially coming from fossil fuels combustion, okay, and some from cement and so on. But this is essentially fossil fuel. And you know, again, you know, this is really a simple chemistry here. We're burning hydrocarbons and we convert it to CO2 and energy. All right, with this emissions to the atmosphere of greenhouse gases, essentially, actually, in this case, it's CO2, we are increasing the CO2 concentration in the atmosphere. And currently we have already exceeded the 410 ppm in the atmosphere. And with this high concentrations, we're increasing the greenhouse gas concentration in the atmosphere. We're you know, this is actually creating entrapment of the energy and the heat within the atmosphere. And as a result, actually, we're increasing the temperature. Okay, so this is becoming a clear, almost clear linear relationship between the CO2 concentration in the atmosphere and the temperature of the Earth. And with that, you know, with the increased temperature, we already actually hear about 1 degree increase since actually the pre-industrial revolution. And this is, of course, you know, for all of us, it becomes actually very concerning. We all of us see the current climate change issues and concerns. And with that, actually, we're running, you know, we're running a lot of predictions and simulations and so on. What, you know, and what if scenarios in the case if things continue as is, where are we going? And if we, you know, if we try to cap the emissions by some percentage, we're gonna hit maybe like this one of the scenarios, like 2-degree scenario, and as part of the Paris Agreement, you know, in case we try to mitigate the emissions by some percentage, where we're going and so on. So we're running different what if scenarios and so on, and the image doesn't look that good, guys. You know, it is you can see here is the emissions here were close to the you know, the 35 billion ton of or gigaton of CO2. And if we want actually to meet the Paris Agreement, limiting the temperature to 2 degrees, we need to actually act right now, you know, and we need to drop the emission by significant percentage. Otherwise, the scene doesn't look that good. And with that, okay, so what can we do with this? You know, you can see actually here that what are our options? You know, doesn't look that good, and the solutions are very, very challenging. Of course, you know, now you can see Elon Musk is thinking actually to go to Mars here, and the only challenge there is that Mars apparently is too cold, and the problem, we don't have fossil fuels over there to heat it up. All right, going back to Earth, and also some additional predictions and outlooks how the energy scene looks like. So this is from BP energy outlook, and it shows, if you like, some transitions that already happened over history from different resources, fossil fuel resources, energy resources. We can see, for example, how the coal, for example, at some point in history or in time was actually the main energy source of energy, and then after that, fossil fuels from oil and gas took over. And then we can start to see now, apparently there is change in the trend where you know, the dependency on fossil fuels will start to decrease, and we're gonna see more contribution from the renewables. But you know, I think it is evident for everybody that, you know, this is not gonna happen very soon, and renewable is gonna take some time to try to displace hydrocarbons. One good news here is natural gas apparently will stay, stay important, and will actually hold the or provide the transition for renewables to start actually to have more contribution and or more effect or more support to our energy supply. Oil, as you see here, starts at some point, to decrease. But again, it's not going to go away soon. It's going to stay, important for our for the energy mix. All right, with the continuation of hydrocarbon, of course, we're going to keep burning fossil fuels, burning hydrocarbons, and emitting CO2 into the atmosphere. And with that, we're going to have more, the issue of emissions and greenhouse gases. And again, from BP outlook here, the way they see it is that you can reduce the emissions into the atmosphere, but you have to come up with, of course, different mitigations plans, including the CO2 capture and storage. And here they look at how much CO2 need actually to the contribution of CCUS, CO2 capture, utilization, and storage. And here they say, all right, we need probably about 4 gigaton of CO2 to be captured and stored in the subsurface. And they come up with different scenarios as well on that. But the idea here, the key idea is that CCS will be important to mitigate the issues of greenhouse gases. And of course, on the top of that, you see in the industry, there's a lot of interest right now in blue hydrogen, blue ammonia, and so on, which is actually converting essentially like methane gas to hydrogen. And with blue ammonia, it cannot survive without having a viable solution, an effective solution for CO2 storage or capturing CO2 and storing it. So the bottom line here is that, this is again, same thing from Shell, for example. I'm just giving some examples here. You go and I think it becomes now very straightforward and clear in all the, within the whole oil and gas industry that the current business model of, producing, burning, and emitting what we call the linear carbon economy is not going to be viable for the future. And everybody right now try to think of some sort of circular carbon economy and so on. And this will not happen without the contribution of CO2 storage. All right, let's now try to zoom in a little bit on Saudi Arabia to give you an idea what's going on there. So here, this is just, I'm showing from the CO2 emissions. This is the cumulative emissions, essentially from fossil fuel over time, over the last 15 years or so. And this is coming from different agencies. And we see here that essentially up to 2015, we can see a growth rate of about 3.5% of CO2 emissions, which is, within that period was almost double the average growth rate worldwide. But since 2015, we can see actually some change in trend and almost a drop by half of the CO2 emission, but it is still going. The good news, it is reducing, but the bad news, I would say here, is still growing. And of course, by like any other countries who are heavily dependent on fossil fuels, I think this is not surprising. So how would the future looks like? Well, it is, again, nobody knows, right? But if you start to extrapolate some lines there and so on, you start to see probably where we're gonna heading, where are we heading actually with these current emissions and so on. So what can you do about it? And as part of the Vision 2030, the Kingdom has already committed to reduce CO2 emissions by 130 million tons per year, okay, by 2030. So this is going to be actually a very important commitment for the Kingdom to reduce emissions. And with that, just recently, 2019, the Ministry of Energy here, they came up with a concept that they called circular carbon economy. And this concept here is, it has actually four pillars in it based on what we call the 4 Rs. And these are related to reduce, reuse, recycle, and remove. Now, if you look at each component separately, there's nothing actually new about it. This is sort of established concepts there, right? So we need to be more efficient. We need to reduce our energy usage and so on, recycling and so on. But I think what's new about this concept is having all these 4 concepts together, integrated together, and forming this framework, okay, for it. And what we're saying here is that we need all solutions. There's no one solo solution here that is able to mitigate this problem and address this challenge. We need the contribution for all viable solutions out there. And with that, here we are showing actually that the remove components through this storage or CCS, and also through reuse, you know, for EUR, for example, or maybe other applications. This technology will be, you know, critical to enable actually this concept. All right, now let's get a bit focus here on what's going on at KAUST. So motivated by the circular carbon economy, and by the way, I should say that there is very obvious and clear commitment from the kingdom actually to address this challenge, and there is you know, based on that and motivated by all this, you know, the current challenge overall for the kingdom or worldwide actually related to energy and environment, we tried from our side here at KAUST to address different aspects of these challenges. And we have, right now, we have an initiative, we're calling it Circular Carbon Initiative. It has different aspects and different focus area related to the 4 Rs that I talked about before, from the capture side, for example, and the remove side, related to you know, from different aspects, different technologies, and so on. And part of this component, if you like, of the circular carbon initiative, we have one is related to what we call the geo-based solutions, and this component has also incorporate different technologies. So all are related to the subsurface. So again, the concept here, maybe as we've seen before, is what we're trying to do is try to, if you like, bend this arrow, you know, from going, you know, from the current scene where we have the linear economy, linear carbon economy, from production to emissions. We're trying to bend it actually, and you know, hopefully we're gonna able to bring some of the CO2 back to the subsurface in the form of maybe a reuse like EUR or geothermal, or in the form of entrapment, with different technologies that I'll also talk about. And of course, there's other activities going on, you know, besides, if you like, the fossil fuel-based energies. There are also other potential for other, you know, energy sources, like, you know, traditional geothermal, wind, and nuclear, and so on. And all this will also, at some point, will include the subsurface component into that. All right, many people are working on this right now, the geo-based solutions, and these are here. We have some names I'm showing here are from KAUST. These are the you know, coming mainly actually from you know, different, you know, we have sort of multidisciplinary backgrounds related actually to the experimental, to geology, to modeling, and so on. And we have also contributors from different universities, you know, from like Texas A&M, Ohio State University, from Dr. Ghorayeb from AUB, from CNRS France, and so on, Martin May from Switzerland. So we're different. Again, this is the PIs, and then if you put the students and so on, maybe we have, I would say, could be maybe basically 30, 40 people working on this area. All right. What I'm gonna do here, I will show, maybe focus on one project that we're working on, and show you briefly, talk briefly about maybe 2 or 3 projects, okay, related to this initiative. So I'll start by the first one, which is we're trying to develop a geological storage atlas for Saudi Arabia. And this work, it is done in collaboration with between several PIs here at KAUST and also people from Saudi Aramco. This work has different components. One component is related to assessing the emissions from stationary sources, mainly related to all related actually to fossil fuel combustions like electricity, desalination, petrochemicals, and so on. And the objective here is just want to get the how does the scene look like in terms of emission map, and so on. And the other components are related to assessing the storage potential in deep aquifers. I'll talk briefly about it and in the coming slides. And also there is potential actually for CO2 mineralization in the kingdom. And this is, I'll have maybe a couple of slides about that. This is mainly motivated by the recent pilot that has been demonstrated in Iceland, known as Carfix. And also we have the potential of CO2 utilization related to EUR, related also to enhanced gas recovery, and so on. All right, so what are we trying to do here? In terms of basically, if I want to put this in simple illustration here, we try to assess the sources where the CO2 is coming from. And at some point, we want to, come up with potential sinks, subsurface sinks, subsurface reservoirs, and so on. And this comes in 2 stages I'll talk about briefly in the coming slides. So at the first stage, we're gonna try to say, okay, what would be the potentially at the regional scale, what would be the in terms of the subsurface, what would be the potential or suitable reservoirs and so on for the CO2 entrapment. And the second stage, we're gonna start to look at site selection and characterization. All right, so let me, okay, so in terms of emissions, I'll show briefly about that. So this is something work that we've started working on it for a while, and it took some effort because there's no reported numbers, from official numbers actually for that. We have numbers at sort of bulk numbers, at the kingdom or the country level in terms of emissions, but we don't have it. We don't have the map for it. And as I mentioned, the map or the spread of these emissions are important for us to try to understand where the big, for example, the areas with the big sources or significant sources, and we can think about this as maybe there be potential, for example, hubs and so on in these different areas, where you can gather and collect the CO2. So what we did in this area is this data actually we gathered from the public domain, from different industries, and we did our, if you like, exercise here to back calculate the emissions and they come up with the with estimates for these emissions. And this included also other areas or other components related to assessing the CO2 concentrations. So not only the volumes, but all these concentrations, which will have actually significant impact on the capture side. In terms of the storage assessment, we did this, or actually this is still ongoing work. We're trying to do this in 2 stages. In one stage is related to the regional evaluation, and the second one is more focused and site specific. Okay, so just briefly on the how we're doing actually assessment for storage. Well, to calculate the storage potential, it is it is actually, we can use this very simple equation, which is just saying that, you know, the volume of CO2, so this is actually here done in mass. So the mass of CO2 that you can store is, you can calculate it based on the volume of your tank or your subsurface reservoir, which is here you have this is would be the volume, the porosity, it gives you the pore volume, the density of CO2 at the reservoir conditions. And this multiplied by some what we call the storage efficiency. So in terms of equation, you know, as engineers, we like actually work with simple equations. But if you look at these parameters here, there is huge uncertainties on them. From one side, for example, we have the subsurface, the volume or the pore volume on the subsurface, and there is always uncertainty about this volume, where you're gonna get this volume, how you're gonna calculate them, and so on. And if you zoom in, also, you know, you're gonna see that CO2 entrapment also is related to different mechanisms like solubility, like interaction with the rock, and so on, that also need to be assessed. And this will reflect on the storage efficiency. So the bottom line here, we have simple equation, but very complex and uncertain parameters to come up with. And as you see here, as I mentioned, you know, to come up with the volume, the subsurface, the volume of the potential aquifers, you need to have actually a good idea about the geology and the 3D modeling on 3D geological model of the subsurface. And this is something that we already started with, but again here we hit the issue of how, you know, getting data and so on, that probably all of you are you know, familiar with this issue, right? As researchers and you know, in the academia, we always have the issue to access actually data. And with that, what we did is you know, we did very extensive actually research and search, if you like, in the to try to find any public domain data published since, you know, decades, you know, and try to collect all this data. And you know, we're trying to digitize this, for example, well logs, depth maps, and so on. And we're creating actually a model for it. So for this, we have included more than, so far, actually more than 140 wells. Some of them, they have the well logs included. We have some of them, or a good number of them, they already have depth and tops and so on. And from the other side, we also, you know, converted, if you like, hard copy maps, you know, and digitize them and so on. So this is, yeah, this is just showing you some example what we've been doing in this area, where you know, we're digitizing maps, we're cross-checking with different sources, and we're converting that to surfaces and putting it on the geological models. And in this case, we're using Petrel for this purpose. And as we develop these surfaces, we're trying actually at that point to go and build the 3D models, like you know, as you see here in this you know, this picture here. And we try to target, you know, the potential aquifers that you know, potentially could be suitable for CO2 storage. Like I'm listing some of them that we're looking at this point. So what's the process here? Well, after we get the 3D model, we're going actually and trying to get also the property of the you know, petrophysical property of the model in terms of like porosity, permeabilities, and so on, or whatever actually we can get actually from the literature. And based on the depth and the pressure data from hydrostatic pressures and geothermal gradients and so on, we try to get the densities of CO2 and eventually try to, you know, calculate the potential volumes. And of course, in this case, on this, you know, for this purpose, we also, it is important to come or understand or assess properly the salinity map. So this is also something we're looking at. The good thing actually of having a 3D model is that you can This is, for example, a salinity map, and then you can just put filters and to figure out, where would be the potentially better area or suitable area for storage and so on. So you can extract or screen out, if you like, the areas or the volumes in the aquifer that are not suitable for that, and you can only focus on the the suitable areas and so on. And once you get that, there is another step where we're trying to use some tools that have already been developed in the to assist other atlases, like this one used for the North America Atlas, which is a simple calculation engine, if you like, just takes the this data in terms of volume, in terms of properties, porosities, and so on, and it runs some Monte Carlo simulations and try to get, if you like, assessment, probabilistic assessment of the storage potential and so on. So this is still a work on progress that we're doing right now, and we're going actually aquifer by aquifer and try to look at it each one separately to try to assess these volumes. And the next step, probably I need to move faster now. The next step that we're working on is we're trying to look at the site selection and characterization. And this is based on what I showed earlier, based on the maps we have there and where we have the high sources of CO2. We try to look nearby and try to find potential sites. And with that, we zoom on in the 3D model that I showed earlier, try to add more data, more logs, and so on, cut sectors, and try to build a more refined model, okay, for this one. And this is just briefly a typical workflow that is well known in the oil and gas industry, where you to build the going actually from the building the geological model all the way from the geological model all the way to the simulation model, starting from building the structural maps and the surfaces, and then the volume phases model, and then all the way to get it to the upscaling and the simulation model. These are just some example to one site that we are working on right now, close to the Riyadh area, and this is again motivated by some good, if you like, geology, and also apparently it is located near some big sources of CO2. Okay, for this one. So yes, so briefly, what we're working on is, again, try to based on these models we're working on, trying to put some potentially good size, like they have good seal, for example, they have the trap, and they potentially have good porosity and permeability and so on for it. So this is at this point where this is still work on progress, and we try to get to a point where eventually we're gonna have the full detailed simulations on it and assessment, in terms also of CO2 leakage risk and so on them. On a separate but related work, also we'll try to look at the potential of CO2 storage or mineralization in Basalt. And this work, as I mentioned earlier, this is mainly motivated by what has been done in Iceland, where they showed this technology, where actually you can just inject CO2 and water in a basaltic formation or volcanic formation, and you can actually show that you can mineralize CO2 and convert CO2 into rock, like in this case it's carbonates. So these are pictures from Saudi Arabia, and we do have here several, like I can show that you can probably see them here in the map. They're different volcanic fields. They are essentially spread along the Red Sea coast. KAUST, by the way, is located somewhere here, and these are just nearby volcanic fields here. Right, this is Professor Aboud Afifi. This could be basically the most experienced geologist for in Saudi Arabia, and he's actually doing a really amazing job actually with in basically studying the feasibility of this technology in the kingdom. So what we're trying to do here is we're trying to look at there's different aspects actually related to this. from one side actually try to because this technology it has some from one side it looks very promising, from other sides also has limitations, especially related to the water, because you need actually water to activate it. And with that, there's different works that we're working on, from characterizing outcrops, for example, understanding the fracture network and so on, because fractures are critical for this technology to work. As you know, like basalt is very tight formation, typically doesn't have much connected porosities and so on. So you have to rely on fractures to to be able actually to have the conductivity in the subsurface and so on. So there's some modeling aspects to it, and fracture characterization and rock characterization as well on this part. On another work here is related now to CO2 EUR. This work is, we try to address one challenge on CO2 injection for EUR, which is typically, a challenge in the industry, where CO2 typically, even at supercritical or in its dense phase, it is still less dense than brine and oil in the system. And as you inject CO2 in the subsurface, CO2 typically actually try to, because of buoyancy, goes to the top of the reservoir and bypass a lot of oil. And this is a challenge because, this makes CO2 less competitive, if you like, to water flood. At least this was typically happens here in the region. And with that, there is currently, we're working on alternative, if you like, technologies where you can, instead of injecting CO2 from, like pattern or pattern type of injection, we try to come up with, different injection scheme where you can maybe try to take the advantage of gravity instead of working against the gravity by injecting CO2 from the top and producing from the bottom. Of course, this is not true technology, but still it has its limitations and the room for improvement, especially in trying to understand the vertical connectivities and so on. And with this work, we're trying actually to build large scale experiments, where like you see this one is more than these cylinders. We're trying to, if you like, mimic what's going on in the reservoir and try to understand, and optimize the different recovery mechanisms and so on it. At the same time, we're also working on different aspects like lab scale experiments, try to understand, for example, in this case, related to CO2 solubility, diffusion in water, and also try to take advantage of other, other technologies like microfluidics and so on, to also try to understand what's going on from the micro scale to the lab scale and so on. Okay, this is another project that is related to CO2. And on this project, this is mainly driven by this Professor Volker, Warenkamp, Finkbeiner, May, and Sar. And these guys are trying to use CO2 for geothermal. The idea here is that instead of using water as a carrying fluid, you can use CO2, and they're actually trying to trying, if you like, to mature this technology. This is not very new. This has been actually sort of started maybe like 10 years ago and so on, but they're tried to come up with the new concepts actually to improve the efficiency and so on of this one. All right, so with that, I'll come to the some closing thoughts about this talk. So the key message here is CCUS, whether CO2 storage or CO2 utilization for EUR or even geothermal, it is a key enabler for circular carbon economy, specifically for remove and recycle, and this will be critical actually for to enable this technology in the kingdom. And as path forwards, we the key message here is that We need all these potential technologies. There's no unique solution that is able to address all these challenges. And for example, just to mention this, like for example, on the western side of the kingdom, you don't find good reservoirs, for example, sedimentary reservoirs that could actually be useful for CO2 storage. But we have basalt and volcanic rock and so on for it. So with that, I'll stop here, and I'll be happy to take any questions maybe as you at the end of this seminar. Thank you.
Thank you, Dr. Hoteit, for a very interesting presentation. I'm sure we have lots of questions at the end of Dr. Kassem's presentation.
Yes,
I would like to give the floor now to Dr. Kassem Ghorayeb to give his presentation.
Yeah,
and you're going to present what we're doing here at Lebanon. I know the scale is very different, but we'd like to see what you've done on this project.
Good morning, everybody. Can you hear me very well?
Yeah, we can hear you.
Yes.
Yes. But as you have mentioned, Professor Ghadar, the scale is very different here. However, I mean, the scale is different, and the maturity of the projects are different, since we've just started the first seed in that regard here at AUB. So I will be talking today about CO2 capturing and sequestration in Lebanon, a full cycle assessment and optimization towards minimizing the country's emissions and footprint. Prior to starting, there's just one comment. Both Hussein talked about, Dr. Hussein talked about the transition, the energy transition scenes from fossil fuel centered to renewables. There are different scenarios. There is the business as usual, there is the net zero, there is the rapid transition. The net zero looks like very unlikely, and I believe things are gonna be just between the business as usual and hopefully more towards this rapid scenario that Professor Hoteit has talked about. One other thing that I think Hussein and myself both belong to this transitional zone, because we're both coming from the fossil fuel, and now we're working somehow on CO2 capturing and sequestration. The good thing about it is the knowledge that people have acquired and the industry in general has acquired in the oil and gas industry, I'm saying, will be of great benefit for CO2 sequestration. Actually, there is an invaluable wealth of information from the gas and oil industry and from the experience in injecting in different types of reservoirs that can be of great benefit of the CO2 sequestration projects. I would like to acknowledge, prior to starting, I mean, this project has been funded by the Munib and Angela Masri Institute of Energy and Natural Resources and KAUST. We have had actually like very generous support from the three ministries in Lebanon who have provided us generously with data: the Ministries of Energy and Water, the Ministry of Environment, and the Ministry of Industry. Actually, it was overwhelming, the type of generosity in providing data with literally unlimited support. And finally, we are, I mean, a big part of what we are doing is relying on modeling, and we are using for that purpose Petrel and Ocean Software Development Framework. I will talk about that a little bit in the presentation. And this was made possible through software donation by Schlumberger. And here, prior to starting, I would like to recognize a large team who, despite all the odds, actually, we happened to start this project in September 2019, and literally 1 month after that, we had the start of this perfect storm in Lebanon, with both nearly the economic problems, I mean, catastrophes, I would say, and COVID-19 hitting the country at the very same time. But despite the odds, the team has been able to do a great job here. There's a team of master students, PhD students, research associates and assistants. And we've got investigators, the Professor Hussam Rassi, Professor Joanna Dumar, Professor Hussein Hoteit from KAUST, and myself. So I'm not gonna just cite all the names, but what I am actually presenting today is simply the fruit of their work. I'm simply merely a messenger here in this presentation. What were the project objectives of when we started the project? And this is what we will be giving this presentation along these objectives. Our objective is to build a roadmap for that can be used potentially by the decision makers and by academics and by researchers in Lebanon on CO2 capturing and sequestration. Our purpose, the purpose of our multidisciplinary research team is to identify and estimate the current and future sources of CO2 in Lebanon, the different potential economical ways of gathering and capturing, gathering and sequestrating that and injecting this CO2. Here we would be considering the onshore and offshore structures means sequestration sites. By offshore would be CO2 could be used for enhanced gas recovery or to be injected in depleted gas reservoirs. And the associated risks of these potential sites. And okay, we could wonder, Lebanon is a very small country. We are a small, consumer and small producer of CO2. So what can be bringing to that picture? We believe that the research that we can do and that we are doing here at AUB can be a model for similar countries to use similar workflows, and hence that would be the collective importance of what we are doing on the bigger scene of CO2 capturing and sequestration worldwide and meeting these sequestration objectives. I will be presenting a few snapshots of what we are been doing in the last few months. I will be talking about the CO2 capturing and sequestration roadmaps review. Prior to starting a project like that in Lebanon, we wanted to review what has been done worldwide. I mean, countries who have built CO2 capturing and sequestration roadmaps, what are the learning experiences from these countries? Then we wanted to review the major CO2 capturing and sequestration projects and what can be learned from these projects so that we can benefit from the pros and avoid the pitfalls in our studies. Then I will be moving to the assessment of CO2 emissions in Lebanon. I will be talking later on the CO2 sequestration modeling, that the exercise that we are undertaking and the way forward in the research being performed here at AUB. So this is the, let's start with the CO2 capturing and sequestration maps. We have studied a large number of maps. Actually, we spent a very long time studying CO2 capturing and sequestration roadmaps from Europe, from the Middle East, from Africa, the Americas, the Asia and Pacific. The key elements of each roadmap that have been reviewed is the goals. For instance, a clear and concise set of targets that, if achieved, will result in the desired outcomes. We have studied the milestones of these maps, the gaps and barriers, the action items that can be taken to overcome gaps and barriers that stand in the way of achieving the goals of the roadmap. And we have reviewed also the priorities and timelines, which is a list of the most important measures needed to achieve the goals and the time frames, into account interconnections among those actions and stakeholder roles and relationships and so on. Some key findings of what we have done, and still work is under finalization is an important similarity among these different CCS roadmaps is their emphasis on improving research and development for the facilitation of commercial deployment. The driving forces, the challenges and opportunities to the deployment of CCS projects differ greatly between different countries, as we will see in the upcoming slide. There are other aspects related to the flexibility in the project milestones, the focus on the full chain projects, and the limited or non-operational supports. These will be provided in hopefully in a publication soon by the project team. Then we have actually, in parallel, we have looked at the major projects, major CCS projects. There are 18 large carbon capture and sequestration projects that have been running when we have started this project. The cumulative operating capacity of the largest scale projects, these 18 projects, is around 40 megaton per annum, actually, which is largely a small number compared to the IPCC's goals to store 6,000 to 7,000 megaton per annum of CO2 by 2050 to achieve the 13% of the world necessary emission reductions. But anyway, so this means the CO2 capturing and sequestration, it has still a very long time to go, actually, to fulfill the objectives for which is being done. And we can see, actually, when we look at these figures, on the left-hand side, there is the status of the large-scale carbon capture and sequestration, together with their numbers and capacities. For instance, if we take a look on the United States, CO2 capturing and sequestration is mainly driven by enhanced oil recovery. Similarly, this is the case in China, in Brazil, in the UAE. In Europe, on the other side, these projects are mainly driven by, these are dedicated projects for CO2 capturing and sequestration. That is, they are not intended for enhanced oil recovery. On the middle, in the middle figure, we can observe the capacity of CO2 capturing at larger scale facilities based on the facilities categories. And on the right-hand side, we see the capturing capacity of larger scale CO2 capturing and sequestration projects in different countries. We have tried to look at, since our focus is going to be in this project, precisely at this stage on the challenges, in the subsurface challenges. These figures show, for instance, some distributions of the properties from these major projects. We've got the porosity distribution, for instance, of the different types of projects, the injection depth at which the CO2 sequestration is taking place, the permeability of the reservoirs, or the geological structures that are used for these type of sequestrations. The distance on this right-hand side, lower corner, we can see the cumulative transportation distance of captured CO2 in large scale in these larger scale reservoirs. The type of formation, sandstone, carbonate, siltstone, we can see that sandstone reservoirs are predominantly the target formation in these type of reservoirs, and the type of cap rock actually in these type of reservoirs. We have taken we have considered and comprehensively studied the different aspects, a couple of dozens of the subsurface and surface parameters in these projects, trying to learn as much as possible from them towards our implementation. I'll move now to the CO2 emissions from power plants in Lebanon. So what we intended in this study is to update the CO2 inventory of the energy and industrial sectors, which was lastly updated in 2015. Actually, this subject is the subject of is master thesis subject for master student Noor Sharafi, and she's gonna actually defend her work very soon in that regard. What we have tried actually, the overall idea is to come up with multi-scenario CO2 emissions under different energy scenes in Lebanon. CO2 emissions being and capturing being a major part of the chain of CO2 capturing and sequestration. And we had one objective is to move the country from a tier 1 CO2 emission calculations to tier 2 emission calculations, hopefully. In this figure, we can see the emissions, CO2 emissions in Lebanon in 2019. Both, for instance, so we've got, this is from the different power stations in Lebanon. There were thermal stations. So this is the CO2 on the left-hand side. We can see the CO2 emission per power plant in terms of kilogram of CO2 emitted by kilowatt hour of electricity generated. And on the right-hand side, we can see the CO2 emission by power plant actually in the same year, but here is plotted in terms of tons of CO2 emitted per year from the different power plants. So what we are intending actually, as I mentioned, from this is to study multiple scenarios. So the scenario that Noor has studied here mainly are the business as usual, the proposed energy structure adjustment by the Ministry of Energy and Water updated electricity power policy paper in 2019, the increase in renewable energy share according to the International Renewable Energy Agency Renewable Energy Outlook for Lebanon 2020, and using different types of fuels. So this is actually it's a fresh figure provided by Noor's work in terms of the predictions of CO2 emissions as generated by the power plants in Lebanon under different scenarios. And in our calculation, in our assessment of potential sequestration, as we can see, we're going to see in the upcoming few slides, we will be considering these different scenarios and the capabilities of the identified sites in Lebanon to accommodate these type of emissions. This is a slide resulting from the work of Professor Dumar, Joanna Dumar, and her team about the identification of CO2 sequestration sites for Lebanon. And here within the scope of our project, Professor Dumar's team investigated the identification of suitable depth, reservoir units, cap rocks, traps, capacities, and the capacity of CO2 sequestration in different reservoirs on different geological layers or different regions in Lebanon. Based on this work, it's been found that the Bekaa and southern regions seem to hold the best or the highest potential for CO2 geological sequestration. Here we can see on this picture actually the different reservoirs. There is the Sheka Formation, the Sannin Formation, the Shuf Formation, and the Jurassic Reservoir Formation that can accommodate the highest, the biggest quantities. There are different criteria that have been used for these selections. Obviously, all of these identified sites will accommodate the requirements of having CO2 in supercritical conditions, and hence having the right temperature and pressure for these conditions to be fulfilled. In this regard, actually, our next step is to build geological models for the select sites using Petrel and to perform the CO2 sequestration modeling in TAF3. I will be talking about this combination and potentially Eclipse in the upcoming slides. Based on within the same framework of the work, 6 different formation samples have been selected by Professor Dumar's team and provided to Professor Hussam al-Rasi's group to study and characterize these rocks to be able to understand their properties and their capabilities and viabilities for the intended CO2 sequestrations. Professor Rossi's have performed a lot of analysis on these rocks, and there are other analyses that are under investigation. So FTIR spectroscopy have been performed on these samples. SEM and different other analyses have been done. Yet to be investigated in the interaction is the interaction of the rock with the CO2, with supercritical CO2. Okay, I'm sorry, I'm looking at some questions coming on the board. And here, so the undergoing work actually is the investigation is of the interaction of the CO2, supercritical CO2, with the different types of rocks in the different formations here. We can see formations from different reservoirs here, actually, the Shuf, the Shekka, Sannin, and others. With regard to our modeling, we are investing a lot of time in preparing the framework, our modeling framework. After some investigations, we have found that our best framework for modeling is going to be using TUF as a simulator. We will be also using Eclipse as a simulator. TUF is Eclipse is developed is a commercial software developed by Schlumberger, and TUF3 is a software developed by the Lawrence Berkeley National Laboratory. Is a multi-dimensional, multi-phase flow simulator, very dedicated to the type of CO2 sequestration projects and geothermal projects. It's very suitable for the type of projects that we are doing. And after investigation, we have found that it has the extensibility and flexibility features that enable us to inject our own physics at one stage if we would like to change or challenge some of the physics implemented. It's an open source code. However, TUF does not lacks the pre-processing needed and the post needed for to build geological models. Our intention is to build geological models for the sites that we have identified in Lebanon. So these geological models will engage some complexities, and so we need a framework to build these models. The best framework to build these models actually is to use a Petrel, since we have Petrel, and Petrel is somehow the industry standard software for building geological models and doing many other things, going from seismic to simulation, and it's among other features of Petrel. So we will be building our geological models in Petrel, but building our geological models in Petrel does not solve our problems because we need to convert these models into TUF. For that purpose, we are building a plugin in Petrel. This is where Hussein, Kassem, and Muhammad Mehdi Aloush are working on it, on building this Petrel plugin to be able to build a geological model in Petrel, seamlessly convert that model into a language that TUF can understand. And once we have run that model, to load back, convert the results from TUF into a language that Petrel can understand and do the visualization in Petrel. So we will hence be having TUF as our TUF3 as our engine for solving our CO2 sequestration and potentially the hybrid CO2 geothermal problems, and having Petrel as a pre and post processor for our work. And this plugin is being enabled by using the Ocean framework for the purpose. This is a work under progress. We have gone a good way through by building building models from Petrel to convert them in TUF. Now we can fully run TUF from Petrel for simple geometries. We're working on more complex geometries now. And the next step is to the way backward from TUF to Petrel. We believe that this plugin will be very important, not only to us, to the progress of our project. We cannot progress without such flexibility, but that will be also useful for other research team in other places, as we claim that this is the first time we are attempting to build such tool actually in the academia or in the industry. And hopefully that will be available for the wider community to be used for the purpose. What are we doing in the way forward? Now we're going to start building geological models for the selected sites and perform the CO2 sequestration modeling in these target sites in Lebanon. We now are going to work on assessing the CO2 emissions generated from the cement industry, again under a multi-scenario conditions. We're working on completing the full cycle of Petrel TAF3 plug-in, the back two ways actually, Petrel to TAF and TAF to Petrel. And we're working on modeling now with this team, actually multidisciplinary team, multi-physics involved in the problem of CO2 capturing and sequestration, and also on the hybrid CO2 sequestration and geothermal using CO2 as the agent that is transmitting energy in this regard. We're working on the different complexities that might arise actually in such injections and productions in the subsurface, with regard to the thermal complexities, with regard to the CO2 rock interaction under different salinities conditions, under different thermal conditions, and especially with regard to real reservoirs where we have a complex geometry and heterogeneities in both the vertical and horizontal directions. I'm going to stop here, and I'll leave it now to the floor for questions for both myself and Professor Hussein Hoteit.
Thank you, Dr. Ghorayeb, for the presentation of this valuable and very interesting work. And with the forward plan, how is it going to be continued? I have plenty of questions here for Dr. Hoteit and you. And some of them, you know, they go about from the risk to the cost, feasibility to partnerships, the way to future. So we will go one by one. The first question is by Professor Muhammad Ahmed about the roadmap for CO2 reduction and sequestration in the future. And what will be the most significant measure, considering the first step is elimination of source? So Dr. Hoteit might start, Dr. Ghorayeb might also want to comment.
Right. All right. So let me say something about this. So currently, if we look at the roadmap, right, there's different solutions or proposed solutions on the table. One of them is related actually to what I showed actually earlier, related actually to reducing, for example, the usage, right, of fossil fuels and promoting renewables, improving efficiency, for example, and recycling and so on. So there is different things that could be done actually to reduce our emissions before actually starting to think about capturing CO2, for example, and so on. But what the issue here that we're talking about is if you do all this, if you implement all these technologies, okay, from again, from using renewables to improving efficiency and reducing the usage, you're still gonna end up with significant volumes of CO2 that will stay, will stay there actually, and you need to find a solution for it. And this is where actually we suggest at this stage actually to try actually to capture this CO2 and sequestering it. Now, in terms of the sequestration part, also there is different technologies on the table. One of them actually to reuse, if you like, CO2, and this is by actually trying to take advantage of it as a commodity. Okay, so from this side, you can use it actually for enhanced oil recovery, for example, or geothermal. And if there is no potential for that, then this is maybe the last resort in this case, actually to use it for storage. So eventually, there is no one solution out there or one recipe, if you like. You know, it's gonna be like a decision tree where you need to decide. You know, depending on the situation, depending on the conditions you have, which option you go there. You know, for this.
Yeah. There is a question about the risk that is associated with the carbon capture wells.
Professor Ghaddar?
Yes, sure. Please.
I think although everybody, it's a consensus now that CO2 sequestration is a necessity to fulfill the objectives of keeping the temperature rise. However, these projects are driven by economics now. So, and actually all the efforts are being made now how to make these projects more economical. In that regard, hence, for instance, the proposal of doing a hybrid like geothermal CO2 sequestration projects. But I think there is quite a high maturity of the sequestration side in the understanding compared to the surface coming from the understanding of the from the oil and gas industry, but yet, for instance, the integrity of cap rocks. So we don't want to inject CO2 and then produce it after a while because we are injecting in the wrong place and there is no, I mean, enough studies. There are no enough studies about the integrity of the cap rocks. These are the associated aspects. But I believe at the end of the day, the most expensive part now in the chain is the capturing. Mm-hmm. So, and here the work of chemical engineering, this is for Professor Ahmed here, chemical engineering has a long way to go on making the capturing technologies more economically viable.
Yeah, that was actually one of the questions by the audience, I think, asking about the cost of CO2 capture, and is the private sector working on this? Can partnership, you know, with between the producers of fossil fuels and companies working in this technology make it economically feasible? So the answer right now, it is not economically feasible, and that's why probably governments are the one imposing or pushing the research forward at that end. Is this correct?
Right. Maybe I can say something about this. So in terms of cost, yes, definitely the bottleneck here actually is in the capture side. You know, and the cost goes all the way from maybe $150 per metric ton to $20, depending what you know, which technology you're using and what you know, where you're capturing CO2 from. If you do, for example, direct air capture, typically, you know, this is going to be very expensive. If you go to the capturing, for example, CO2 from you know, from high concentration sources like gas processing units, for example, or hydrogen and so on, the cost may go down to maybe $25 per metric ton. So it goes all the way, actually, you know, within this range. The key here is what you mentioned, Professor Ghaddar, is about, you know, the role of the you know, private sector versus the governments and so on. So up to this point, you know, if you look at it in the worldwide, you know, this is definitely a worldwide problem, is that for the private sector, up to this point, there's no real incentives out there. Okay, meaning that, you know, even if they capture this CO2, up to now, there is no market for it. Okay, so there is no, for example, who's from one side, who's gonna actually be able to pay for it to buy this CO2, and the other side is from the government side. In government sides, I would say, you know, most of the countries out there, there is there is no policy in place to define, or to set, if you like, the market for CO2, as a commodity or taxes and so on. So this is still a non-mature area, and definitely, many countries out there are still working on it. And also should mention that this is not one country's problem, right? So even if one country find a policy and the neighboring country is still emitting CO2, there is not much value out of it. So it has to be a collaborative, if you like, effort on this part.
Yeah. I have a couple of questions from Mr. Nasser Daw. He's asking, can you please talk about the feasibility? The question is to Dr. Hoteit, to ask about the feasibility of KSA Line City, if possible. And he was saying that a great place to look into is the rocks in the Sultanate, in Sultanate Oman. The rocks there in Ibra were studied by scientists of having the capacity of removing CO2 from air and transform it to stones, and hence be able to store hundreds of years of human emissions. Yani, these are some of the things. Anyway, so if you could answer this.
Well, on the Line City, I'm not really in a position to talk much about it, because up to now we don't know really much about it, and except what has been announced out there. But what we know is that NEOM overall, they're trying actually to to build a city where they can be fully green. Okay, in this case,
yeah.
they're gonna be actually using renewables from solar to wind and so on, and try, if you like, to be less dependent on fossil fuels. So this is what we know up to now. Now, how this gonna be realized, this is something to to be seen in the future. On the other questions for Oman, yes, so Oman also has very basically they have, in terms of the geology, they have also the mafic and altamafic formations, for example, and rock that is reactive rock, similar to the basalt, for example, and volcanic rock. And this is also, yes, there is also potential there actually for CO2 mineralization and so on. So in theory, there is actually, it is there, this can be done. But again, in practice, how can you make it, apply it, or deploy this technology at large scale? This always actually a challenge out there. So
yeah. I have a question from Dr. Ahmed Harb. How will you be able to model the onshore reservoirs in Lebanon, knowing that there's lack of data in terms of wells and other seismic data? I think Dr. Kassem probably would like to answer that.
I think this is a good question, Ahmed. Yes, we don't have a lot of data, but we have as much as possible. What we are, this is where is the role of Professor Joanna Dumars. Joanna, with her experience in aquifers in Lebanon and all the research, great research she's doing there. She has built a lot of understanding about these rocks. We don't have to have oil and gas wells to understand these reservoirs. We might have water wells and understanding these reservoirs. That's one from one side. And from the other side, as long as we have a high level of review of their capacity, we can do uncertainty analysis and try to capture the capacity and the sequestration viability under uncertainty in these reservoirs.
Yeah. Mr. Muhammad Da'i is asking, is the carbon capture and sequestration a short-term temporary solution to mitigate CO2 until we can transition to renewable energy production? Is this something that we can see for long-term sustainable future, or not?
Is it for me, this question, or?
It is a general question. Like, we work on the technology, the advancement, and so on to solve some problem where we probably know that the highest carbon emitter is electricity production or electricity generation from fossil fuels, according to the chart you have shown.
Sure.
So
Yes.
if we eliminate the need for that, maybe that will also reduce the need for the carbon capture.
Depending on what we define. Go on, Hussein.
Yeah, so I think now it becomes very clear, you know, that, you know, if we continue business as usual, as Kassem actually talked about, we're gonna actually hit, if you like, we're not gonna meet the Paris Agreement. I think this is becoming obvious, and within maybe like it is actually coming very soon. Within 15 to 20 years, actually, we're gonna hit the 2-degree C. Okay, and in this case, without doing anything, you know, the do nothing scenario in this case. So CO2 capture and storage, yes, I would say it will help actually in the transition, right? In the transition, because renewables, if you think about it, renewable is not ready in the coming near future, in the coming, let's say, 15 to 20 years, is not ready to take over. Okay, up to now, fossil fuels, it is used more than 70% of our energy right now worldwide is coming from fossil fuels. So to have the renewables ready to take over is going to take time. Okay, even with the accelerated scenarios and so on. And within this time, we cannot afford to keep emitting CO2 in the same way, you know, same way we're doing right now. So this is where actually CO2 capture and storage would be helpful in the transition period. Yes.
Yeah.
I would like to add one little thing here.
Yeah.
As Hussein has mentioned, under the actually most optimistic scenario, the world in the coming 30 years will be rely mainly on fossil fuel for the energy supply. Under even the most optimistic scenarios, the good news, as Hussein has actually mentioned at one slide, that we're going to be relying more and more on gas rather than hydrocarbon oil. And gas is, by definition, is like semi-green. The emissions from gas and the pollution from gas is drastically less than hydrocarbon oil. So in any case, depending on the long-term solution, if we mean long-term, 100 years, nobody knows how technology is going to do in 50 years. But in the foreseen future and under some linear kind of thinking, if things continue like that, very likely, if we don't rely on CO2 sequestration, we're not going to be able, by any standard, to meet economically the emission targets.
Okay. I'm getting too many questions, you know. I think everybody is, the topic is new to some of our students as well. There's a question about the risk associated with these CO2 wells. Like you put them in a storage media, and how do you make sure that these storage wells don't become a source of CO2 release? This is one of the questions.
I'll take part of the answer, and Hussein may add to it. Sure. One major part when we do sites identification is the study of the caprock integrity. So this is one major aspect. We don't go and just inject anywhere. There should be a seal, actually. There should be a reservoir. There should be porosity, and there should be a seal in this study. But this is the single most important risk factor that is studied. Is we don't want what we are injecting to be produced at one stage. Regarding the seismicity, what we apply here applies to every single injection we do in oil and gas reservoirs. So in every single injection, gas injection, or water injection, for instance, in these shale gas reservoirs, that risk exists. But this is a problem that's pretty understood.
Yeah. All right. There's another question to Dr. Ghorayeb. Did you conduct any study concerning the cost and compatibility of CO2 capturing techniques with currently operating electricity generation plants in Lebanon? And did you compare this cost with the cost of investing in clean renewable energy?
We did not do any cost-associated investigation yet.
It's something that could come in the...
That's going to come at one stage.
And another question from Raghida Waida. Could the captured CO2 be a source of power? Now, for a chemist, the answer is clear, but...
Well, capturing CO2, of course, it is very energy intensive. It requires takes energy. It's the other way around. And for a facility, let's say power plant facility and so on, if you wanna capture the CO2 emitted from a facility, typically it's gonna take about 20% consume 20% of the energy produced from that facility. So this is why it is so very expensive.
Yeah. One more question. How do you believe Lebanon as a country government can learn from Kingdom Saudi Arabia in terms of CO2 capture? I don't know what we can learn.
But I think what we are doing, the most important thing is what we are doing. So this type of collaboration between, for instance, AUB and KAUST is the sort of learning curve, actually. So
yes,
is benefiting from each other's. So put aside everything, other aspects, governmental aspects. This academic collaboration, I think this is a great thing, at least.
Absolutely.
Yeah.
Just to add one thing on that is that this challenge, the energy and environment challenge, it is actually beyond the capabilities of a single country. All right. So this is really a very challenging problem, and this is still new, right? So of course the industry, oil and gas industry, has implemented or they have deployed the CO2 injection and so on, but this is mainly in the context of oil production, and this has not been yet implemented at if you like significant industrial scale in aquifers, for example, or other technologies. So this is still a non-mature area in this regard, and this requires, if you like, the efforts and the contribution from everybody. All the research from the research side, and also from the governmental side.
I have another question from Dr. Muhammad Ahmad. He's saying, isn't it better to use CO2 to grow algae and microalgae in bioreactors or CO2 methanation? This way, you are converting CO2 to more useful products. So this is like, the subsurface and the atmosphere.
Yes, I think, this is, of course, one technology that has been actually investigated, long time ago. Even oil companies actually looked into it in the past, and it has two challenges. From one side, it is expensive. It's still, it's not competitive, if you like, to fossil fuels like gas, for example, natural gas and so on. So this is from one side. From the other side, if you think about how much CO2 you're gonna actually consume, okay, from the algae, for example, is sort of like pennies, in this case. So it's not gonna be,
it's different scale what we're considering.
The emissions, yes. So that we're now, the volumes that we're emitting is definitely at way larger scale than any algae can consume for it. But this is definitely one area that is we still need it. We still need all potential solutions out there. We need the contribution from all those. Yep.
Well, I don't see any more questions here on the screen, but we can have room for one more if anyone is asking. Yeah, there is one from Mr. Kamal Halawi. He's saying KAUST is a beautiful place. It was supposedly a private message, so he has toured it once. this is not a question, but he's just commenting on KAUST.
Yeah, well, I agree with that. Definitely, we're so lucky, I can say here, to have this place. It is very nice place. It is very nice community, and we're so privileged here with all the resources actually we're getting here from KAUST, from the kingdom. It is really unmatched, I would say, and what we're trying to do, I think, from other side, the way we try to give back is actually working on this interesting, projects and the research that hopefully at some point will get to implementation and get to something useful out of it.
Yeah, thank you for that comment. Any university on a seashore would be a nice place, and that also applies to KAUST and to AUB. So I hope this is the reason for continued collaboration on this project. Somebody is asking Dr. Ghorayeb about the tool that he uses for the scenario simulation and to model also the policies. The FWAT scenario, so that you assess what you need to implement as policies.
The policies, to be honest, that's Noor's subject. For the modeling itself, in scenario simulation, I'm not sure whether, I think Sophie Schlela.
Yeah, Sophie Schlela.
I'm not sure, Sophie, where you're asking about how we are modeling the subsurface. If so, Noor is answering on the policy part that we are using LEAP.
Yeah.
And and Noor has trained herself on using LEAP, and she's using LEAP for that. On the subsurface, we will, as I mentioned, we will be benefiting from a great framework of understanding on modeling from the subsurface we have gained from the oil and gas industry. For instance, both Hussein and myself worked for a very long time in reservoir simulation, and my other hat actually is field development planning under uncertainty, where we try to accommodate for the subsurface uncertainties in terms of porosities, permeabilities, connectivity, faults, and so on and so forth on the oil and gas optimization. So we will be applying the very same frameworks with regard to CO2 sequestration. It's the exact same thing, but we are replacing production of oil and gas and by injecting CO2. So there we are injecting CO2 to produce more oil and gas. Here we are injecting CO2 to just keep it there.
Okay. Everybody is saying thank you to the panelists, but I would like to say also thank you for this, not just interesting presentations that opened our eyes to a hot research topic area, but also the lively questions and interest from the audience. Some are professionals and others are students. Some students are asking me to put some quiz questions by the end of the seminar to just see that they captured the main concepts, but we will keep that for class. All right, I'd like to thank everybody for attending this presentation, and hope to see you in future seminars, and maybe we will visit KAUST in person now that I'm hearing about the beautiful campus there.
Yes, absolutely.
Thank you all. Thank you very much. Thank you, Dr. Hussein, and thank you, Dr. Kassem.
Thank you, Nasreen, for arranging this interesting meeting.
Absolutely. Thank you very much, and you're definitely very welcome. And also, it's always a pleasure to visit AUB as well. It also
hopefully when COVID-19 restrictions are just over.
Exactly. Yes.
In no time, inshallah.
Inshallah.
Shukran كثير. Thank you, everybody.
Thank you, everybody.
Thank you.